Hi everyone, this is Lab 7.05, determining the identity of an unknown metal through measuring its specific heat. So what I have here on the front desk, you can see a hot plate with a beaker of water. That water is almost at its boiling point. I have a coffee cup calorimeter. All this is, ladies and gentlemen, is two styrofoam coffee cups embedded in one another with another small piece of styrofoam to try to insulate whatever gets put below here. Okay, now notice that there are some holes. The reason why we have a hole inside of our calorimeter is because we are going to need to put in a thermometer so that way we can read the temperature. So with that being said, ladies and gentlemen, the heat transfer in this lab will not be 100% efficient because, as you can see, there are different areas for the heat to escape. And we'll talk a little bit more about that as we continue on into some of the post-lab for this actual lab. So, what do we need to know first? Let's get some of our preliminary data. Actually, there's my unknown piece of metal. I thought I lost a piece of metal. So here's our unknown piece of metal. Small. Okay. First thing that I need to know is the mass of this metal. So I'm going to open up my balance here. We'll jot down the mass on the front board. You can jot it down in your data table here as we go. 30.5138 grams. Make sure I don't mess up any numbers. 5139. I'll put the data in the description of the video as well. I know it's sometimes hard to read when I write on the front. Okay? So now, at this point, I am going to drop our piece of metal into the hot water bath. The reason why we're going to do this is so that our hot piece of metal can heat up to the same temperature at which water boils. If we leave this piece of metal in our hot water bath for approximately 10 minutes, well then we can assume that the piece of metal has the same temperature as our boiling water. Just a reminder, at what temperature does water boil in Celsius? That would be 100 degrees Celsius. So to avoid splashing myself with boiling water, I need to get a test tube holder. So I can safely drop this in the beaker. Okay. So while that is heating up, ladies and gentlemen, I am going to complete a couple of other portions of the lab here. So we're going to need to know, and as I can already see, I put the mass of the metal in the wrong spot, so let me change that. Okay. So how this is going to work is we are going to put a specific known amount of water inside of our coffee cup calorimeter. I know that the lab document itself says 40 milliliters, but we're going to use 50 milliliters. In addition, the lab document tells you to put your coffee cup calorimeter on the balance and then to hit 0 and then to measure the mass of your water. That's unnecessary, ladies and gentlemen. Water has a density of 1 gram per milliliter. So if we measure the volume of water used, that will be equivalent to the mass of the water. So if I could find, thought I had everything up here, but guess I did not. I need to get a graduated cylinder so I can measure out 50 milliliters of water. Okay. I'm a little bit less than 50, that's okay. Just what's important is that we jot down an accurate volume. All right. 48.2 milliliters. So we are going to be putting 48.2 milliliters of, I just got water out of the tap, so about room temperature water, inside of our calorimeter. Now, when we make the transfer, ladies and gentlemen, it is going to be important that we have enough water inside of the coffee cup calorimeter to completely cover the metal. Upon looking at 48.9 milliliters, I am seeing that this is not going to be enough water, so I'm going to change our amount of water again. We're going to try to go closer to 100 milliliters of water. So bear with me as we change our size of the graduated cylinder. Okay, second time's the charm. I'm actually going to write down the volume this time. This should be good to go. All right. Draw the waters out of here for the first time. There we go. All right. Let's see where our volume is at now. We are at 98.9 milliliters, which is the same thing as 98.9 grams of water. So now what I'm going to do is pour the water into the calorimeter. Perfect. Now we have enough water inside the calorimeter, so that way when I put the piece of metal inside the calorimeter, the piece of metal will be completely covered by water. And that's an important aspect. We want the calorimeter, or we want the piece of metal to transfer its heat energy to the water, not the air above the water. So that's why it's important to have enough water inside of the coffee cup calorimeter to ensure that the piece of metal is completely covered. Okay, now we are also going to need to find the initial temperature of our water. So I'm simply going to take the thermometer, put it in the water, get a measurement. So as we wait for that to go, you can see our piece of metal is still in the boiling water. I'm not exactly sure how long it has been, but once again, we are leaving it in the boiling water so that way we can assume the initial temperature of our metal will be the same as that of boiling water. All right, let's take a look at our initial temperature of the water in the coffee cup calorimeter is 21.3 degrees Celsius. 21.3 degrees Celsius. Okay. We've talked about the initial temperature of our water, ladies and gentlemen. We are assuming, because we're not actually going to be able to take the initial temperature of the water, or of the metal, we are assuming it is the same as that of our water. So because water boils at 100 degrees Celsius, we are going to assume that the initial temperature of the metal is 100 degrees Celsius. Okay, so now let's talk a little bit about what's going to happen once I put the hot piece of metal into my coffee cup calorimeter. Okay, well, what's going to happen? We know that hot objects, like our piece of metal, transfer heat energy to cold objects. Heat flows from areas of high to low in terms of kinetic energy. Okay, so we are going to see a release of heat by our metal. Remember, a release of heat is simply represented by a negative Q value. So the opposite value of Q of our metal. Now, we are going to make an assumption in order for this lab to work. When we go through the post-lab, we'll talk about why this assumption in reality doesn't always work. But for the purposes of doing this lab, we're going to make the assumption that 100% of the heat energy that is transferred from the metal goes into the water. So the heat energy released by the metal will be equal to the heat energy absorbed by the water, and this is the water in the calorimeter. How is this helpful? Well, we know the specific heat of water. Remember, Q is equal to MCAT. We know the mass of water used was 98.9 grams. We know the specific heat of water. That's a known value, 4.18. We are going to be able to figure out the change in temperature of our water, but that's not until after we put our piece of metal inside of the coffee cup calorimeter. So using this assumption, we are going to be able to determine the specific heat of our unknown metal, and in turn, the identity of our unknown metal. Okay? I'm going to continue to let our unknown metal heat up for, say, about 2 to 3 more minutes. Feel free to fast forward the video 2 to 3 minutes for the next piece of the lab. this point, we are ready to transfer our hot piece of metal into the coffee cup calorimeter. So what I'm going to have to do is, as quickly as possible, get our piece of metal from the boiling water to our coffee cup calorimeter, and then I'm going to need to put the top on and put the thermometer in so I can see the highest temperature that our water inside the coffee cup calorimeter reaches. I'm going to try to do this as quick as I can without burning myself or spilling anything. Now, before I do that, let's jot down our initial temperature of the water. Boiling water is at, let's jot down the initial temperature of the metal. We already did. Perfect. Okay, we're ready. 100 degrees Celsius. And now it is my job to determine the highest temperature that is reached by the water inside of my coffee cup. So I have to watch carefully for when this stops, or for when the temperature stops going up. Right now we are at almost at 24 degrees. Shaking it around a little bit to mix up some of the particles and allow them to collide a little bit more frequently. We're above 24, approaching 25, above 25, we've surpassed 25. Will we hit 26? Let's say 25.6 is where we're at right now. Not done yet. Got to see if this the highest point that is achieved. Closer to 25.7, 25.8 in that range right now. Might be slowing down. I don't think we're going to hit 26. 25.8. 25.9, we're really close to 26. 25.9 may be as high as we get. Give it another second up. 25.9 is what I'm seeing. I don't think it is going to go up from here. Okay, so we now know the final temperature of the water. 25.9. Just do one more quick double check, make sure it didn't go up. Actually, ladies and gentlemen, I may have been a little bit premature there. Now, when I get back down to eye level, it's slightly below the 26. That's why it's important, always important to measure at eye level. When you're looking down on it, things can be deceiving. Okay, so I get down to eye level, and I agree. 25.9 is the proper measurement for the final temperature of the water. Now, here's where we have to make another assumption. We don't have a good way, or we don't have a way of measuring the final temperature of the water, or of the piece of metal. I can't just put the thermometer on the piece of metal and say that's the temperature of the metal. So we have to make another assumption. We have to assume that the final temperature of the metal is the same as the final temperature of our water. Now, why can we make that assumption? The metal is in the water currently. So, similar to how we assumed the initial temperature of the metal when it was in the boiling water, we can assume, because the metal is inside of our coffee cup calorimeter, that it is the same temperature as the liquid or the water inside of our coffee cup calorimeter. So this would also be 25.9 degrees Celsius. Now, to find our change in temperature, because that's what we need when using this equation, we would simply subtract those values. I will let you do that on your own time. So at this point, you have all the data that you'll need to determine the specific heat of the unknown metal. Go ahead and crank through the calculations to determine the specific heat of the unknown metal. We will then come back together as a class and discuss some of the error analysis associated with this process. Good luck.